Greetings of the day, dear students. In this video, we are going to discuss about the Swinburnes test or no load test, one important test. If you are having laboratory for this course, right, you are going to do this experiment in your laboratory, right? Now, we will discuss what are the different variables we are having, what are the different data we have to observe while performing this test, and how to calculate the efficiency and how to predetermine the motor efficiency at any other loads. And also we will discuss one example problem so that you will understand in a better manner how to calculate the efficiency and what are the different losses. All those things will be discussed in this video, right? Yeah, observe, dear students, this is Swinburne's test or no load test. It is also called an indirect test to calculate, one second, to calculate the no load losses. The main advantage of this test is it is very convenient and economical, and also the efficiency can be predetermined at any load without really applying the load, right? Whether it is at 1/4 load, half load or full load, we can assume for those loads we can calculate the efficiency without really applying the load once you know the stray losses. Right? Now, one more important point, this test should not be performed on this cannot be performed on DC series motor. Why? Because with respect to the series motor, what happens is if there is no load on the motor, it will reach or attain very high speeds at the starting if there is no load, and also it is going to damage the machine. Also the machine will get damaged. For that sake, this method, Swinburne's test or no load test, is applicable to those machines where the flux and speed remains constant. The flux and speed remains constant. So it is particularly suitable for shunt motor or compound wound motor. It is particularly suitable for shunt motor or compound wound motor. Now, coming to its procedure, what happens is initially the motor is run at no load, and slowly we will make the motor to reach its rated speed, most of the time some 1500 rpm, right? Now under no load also still the motor draws some input current, right? That current is indicated with the variable I naught, no load current, and this is measured with an ammeter. Similarly, the current flowing to the shunt field winding is measured with an ammeter. Now, from our previous basics, whatever the current is drawn under no load condition, that is indicated with variable some I naught, some part will flow to the armature under no load condition, let it be IA naught, and some part of current will flow to the shunt field winding ISH. Now if you observe, I naught is equals to the current drawn under no load condition will be equals to the I naught will be equals to the IA naught plus ISH. From this basic, we can calculate no load armature current IA naught equals to how much? I naught minus ISH. I naught minus ISH. So from this formula, we have calculated no load armature current. Now observe this diagram at this point. So this is the motor armature A. You will have in your lab on its nameplate, and this is the field winding Z, right? So the terminal voltage, applied voltage is V, and it is drawing some current, no load current I naught. Some part of that is flowing to the armature IA naught, and some part will be flowing to the field winding ISH. Now the input power, the no load input power is equals to the V into I naught. What will be the armature input under no load condition? V into current drawn by the armature IA naught. But what about IA naught? I naught minus ISH if you apply KCL. Now the power input to the shunt is V into ISH. Now under no load condition, whatever the power that is given to the armature, it is going to supply the iron losses, mechanical losses, and no load armature copper losses. Before this watching this video, you should be familiar with the different losses in DC machine. Different losses in the DC machine, right? Yeah. Now, whatever the total input is given minus no load armature copper loss, because I square R losses, I square R under a no load, what is the amount of current drawn by the armature, IA naught, and the resistance of the armature will simply give you the no load armature copper loss will be equals to what? Constant losses. This point is very very important. This point is very very important. In this entire discussion, the total input minus no load armature copper loss will be equals to your constant losses, will be equal to your constant loss. Now, by we know the constant losses, what about efficiency? Output power by input power. It can also be written as the output is nothing but whatever the input you have given minus losses will be available as output. So output equal to input minus losses by input, or you can write like this also, output by your input is nothing but output plus losses, right? Either the formulas are okay. Now using that formula we can calculate the efficiency. So this is how, these are all the different formulas from the data obtained from the Swinburne's or no load test. We can predetermine the efficiency of a given machine. Clear? Now let me do a small example. We will understand it in a better manner. Right? Yeah. At last our target is to find out the efficiency. A 250 volt a 250 volt DC shunt motor takes 4 amps at rated voltage on no load. The armature and field resistances are zero point 0.5 ohm, 250 ohm respectively. Calculate efficiency of the motor for a load current of 40 amps. If it is drawing 40 amps, what will be the efficiency of the machine? That is what he is asking. But the motor is drawing 4 amps. Under no load, without any load itself, it is drawing some 4 amps. From this, we should be in a position to calculate the constant losses. So, with respect to shunt motor, some I naught is the no load current drawn. 250 volts is applied. This is the motor armature A, and this is the shunt field winding Z. The resistance is given 250 ohms. The terminal voltage V equals to 250 volt. No load input current I naught. From the data given, dear students, please use the proper variables. It will be very useful and helpful to you. Once we use the proper variables, so many problems will be solved, right? Yeah. No load input current I naught is 4 amps. Armature resistance variable is RA 0.5. Field resistance, the variable is RSH 250 ohms. Now efficiency of the motor, if armature draws 40 amps, if IA equals to 40 amps. What about efficiency? Output by input. What is output? Input minus losses by input now. Sorry, input minus losses. But what about losses? Constant losses plus variable loss. Depending upon the load, current, IA square RA will change. Right? Now, whatever input under no load condition without any load, this point is very very important. In this entire discussion, this point is the key point. There is no load. Whatever power is given is wasted in the form of constant losses. And no load armature copper loss. But what is the input given under no load? V into I naught. V is already given 250, 4 amps. I naught value is 4. So 1000 watts is given as input. Now what about shunt field current? V by RSH. V is 250 divided by 250. So the current is 1 ampere. Once you know ISH and I naught, what about armature current? I naught minus ISH, 4 minus 1, 3 amps. So the armature copper loss, I square R, I square R, IA naught square RA, 3 square into 0.5 at armature copper loss is 4.5 watts. Now the constant losses of the motor will be total input minus constant losses of armature. Constant losses of armature 1000 minus 45, sorry 4.5, it is 995.5 watts. Now what is the current drawn? If the load is when the load is applied, if the load is applied 40 amps, at that time what will be the armature current IA? I minus ISH. I is given 40 minus ISH, we have found 1 ampere. 40 minus 1, 39 amps. Now armature copper losses at load, I square R, IA square RA, armature current IA square RA, IA is given, sorry, we have calculated 39 square into 0.5, so 760.5 watts is the armature copper loss at load, right? But what is the motor input? V into I. At that time what is the load current? 40 amps, 250 into 40, 10,000 watts is the motor input. Now what will be the total loss? Constant losses plus armature copper loss at load. Constant losses we have derived without any load. How much it is? 99.5 watts. 995.5 watts plus losses at load 760.5 variable. Constant plus variable loss. This point is important in this entire discussion. If this goes wrong, entire problem goes wrong. Clear? Yeah. 1756 watt. 1756 watts. Now we know the input power. We know the total losses. Easily we can find out the output power. Output power is nothing but input power minus losses. So 8244 watts. What will be the efficiency at 40 amps? Output by input 8244 by 10,000. It is 82.44%. 82.44%. So like this, at different loads, same problem we can do for 10 amps. If the load is drawing 10 amps, we can do. Constant losses will be same. IA square RA will change. Based on that, efficiency also will change. For different load currents, we can calculate the efficiency, predetermining. This is what called predetermining the efficiency. Once we know the constant losses, the efficiency of the motor can be predetermined at any load using the Swinburne's test. Another name is no load test. No load test. Clear? So this is what all about the Swinburne's test, dear students. Right? I hope you understand. Please practice the problem so that you will understand it in a better manner. Right? Please don't be afraid of doing the problems. Be confident. Understand the data. Take proper variable names. Substitute. Do the calculations. Don't think that for a final answer itself, if you get exact this answer itself, if the problem is given, don't think that for this, if you get exactly 82.44 only, if the problem is given for 8 marks, you will be given 8 marks. No. So many marks will be allocated. while evaluating your paper in your exam, with the paper evaluator will check whether he has written the data given or not, if any suitable figure required is not, whether he has written the formulas or not, has done the substitutions or not, later calculations and later final answer. The common mistake students are doing is the moment they see the problem, they are skipping that question. They are making it as a choice. Only they are interested in attempting the theory questions or derivatives or some definitions. So please practice the problems also. Don't be afraid of the problems. Really, frankly to say, by attempting the problem questions itself, we can score the more marks. Yeah, that is the fact, right? Okay, students, I request you once again to share this application to as many students, friends in other colleges, same, right? As many students as possible so that it will be helpful for me and also for the students also, right? Thank you. If any topics are missing as per your syllabus in this course, please send in a WhatsApp message. Immediately it will be added. Within 2 or 3 working days, the videos will be added, right? If any topic is missing as per your syllabus. Thank you.